All right, so we're going to talk about atomic radius, size of an atom. All right, there's two things we need to know. Number one is that atomic radius decreases across a period, also known as a row on the periodic table, and it increases down a group, also referred to as a column. Now, that first statement should be a little bit counterintuitive. You know what that phrase means, counterintuitive? What does it mean?
It means that it's counterintuitive.
Okay. Very good.
It
It means it's not what you would think it is, right? Like, so a logical thinking person would come to a certain conclusion, and that conclusion happens to be wrong, right? So if you look at the second period here, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, okay? Intuitively, at first glance, you would think that those atoms would get larger, okay? Because lithium has 3 protons and therefore 3 electrons. And beryllium has 4 of each, and 5 of each, 6, 7, 8, 9, 10, right? So you would think by the time you got over here, when there was 10 protons and 10 electrons, that this would be a much larger atom than lithium. That makes sense? Okay? So if I had a bunch of sacks up here, and I put 3 apples and 3 oranges in the first sack, 4 apples and 4 oranges in the next sack, and all the way over here till I had 10 apples and 10 oranges in this sack, okay? I'm going to have a much larger sack over here than I had over there, right? That's intuitive. It would work that way. It doesn't work that way with atoms because this has to do with electrostatic attraction. Okay? We'll write that little phrase down. Electrostatic attraction. We also want to refer to that as effective nuclear charge. Effective nuclear charge. So what happens is protons and electrons, hopefully you learned back in elementary or middle school somewhere, that a positive and a negative thing attract each other, right? Everybody good with that? What do 2 positives do? Repel, and 2 negatives do what? Repel. All right. So these 3 protons are attracting these 3 electrons. They're holding them in the atom, right? But then when you go to 4 and 4, there's more attraction there. So that kind of shrinks just a little bit. And then when you go to 5 and 5, it shrinks some more. 6 and 6 shrinks a little more. And there's 7 and 7, and 8 and 8, 9 and 9, and 10 and 10. Okay. So due to electrostatic attraction, or what we call effective nuclear charge, the atoms get smaller going across each given period. Okay. More protons and more electrons makes for a smaller atom. Doesn't make sense when you first think about it. You got to remember that protons are really, really small. Electrons are so small that we don't include them in the mass of the atom. We don't even bother adding them into the number. Okay, they're so tiny. So just adding that as an object, think of it as an object, doesn't really mean anything. But their electrostatic attractions are very significant. Their actual mass and volume is insignificant, but their electrostatic attractions are very significant. Okay. All right. Now, going down a group, atoms get larger. Okay. So here, if you just take the first group, this has a 1s and a 2s. This has a 1s, 2s, 2p, and then a 3s. And this has a 1s, 2s, 2p, 3s, 3p, and then a 4s, right? 4 is bigger than 3 is bigger than 2, not just numerically, but also in terms of physical size of orbitals. So, for example, model right here. I mentioned the other day, this is an s orbital. Is real simple in shape. It's just a sphere. All right, but there is a difference between a 1s, a 2s, a 3s, and so on. If this is a 1s, then a 2s is a little bigger, and a 3s is a little bigger, and 4s, and 5, and 6, and 7. Okay, so if an atom has electrons in the 4s, it's going to be larger than an atom that only has electrons in the 3. It's kind of like layers of an onion, but not exactly. Okay, but that's a sort of a good analogy, but then in ways it's sort of a bad one. All right, so atomic radius increases down a group. All right, and this has to do with energy levels. What we're going to have to do by Wednesday is be able to take a given list of atoms and tell me which one's the smallest, which one's the largest. And then we're going to talk about something called ionization energy, so tell me which one has the highest or the lowest. Basically multiple choice, okay? What you have to do by Thursday, and what the hard part is you have to be able to explain why that's the case, okay? So there's a trend, and then there's the reason why, okay? There's a second trend and the reason why, okay? So we'll have to practice with that some. Okay, that's our first periodic trend. Here's our second one. Ionization energy. This is the energy, I'll get a good definition on this. Energy required to remove an electron from an atom. Okay, there's two trends here. This is going to increase across a period. Is going to decrease down a group. All right, so higher ionization energy means more difficult to remove. And we'll jot that little phrase down. People tend to get this a little backwards and confused. Higher ionization energy means that the electron is more difficult to remove. Higher ionization energy means the electron is more difficult to remove. So, if you go across that any given period, we'll take our period number 2 here as an example. If you go across that period, the electrons get more difficult to remove because there's more protons holding them. So if I'm an electron in neon, I've got 10 protons holding me in. It's going to be harder to get away than if I'm in lithium and only have 3 protons holding me. Okay? So as you go across a period, it's more difficult to remove the electrons, so the ionization energy increases. If you go down a group, they get further apart, so it gets easier. So you ever play with magnets? Okay, if you take magnets and the closer they get to each other, the more they pull, right? The more you separate them, the less they pull. So the further an electron is away from the nucleus, the less it's held. So like this electron, for example, is considerably further away from the protons than this one is from its protons. So this one's much less tightly held. It's easier to remove it. It's got a lower ionization energy. So the reasons here are essentially the same as atomic radius. It's effective nuclear charge, and energy levels, which determine the distance. Okay? Question about that right quick? All right. This is for me right quick. Look at your periodic table. Figure out which atom would be the smallest and which would be the largest. Periodic table. All right, what's the smallest? What's your first inclination when you say what's the smallest atom? One with the least stuff in it? That would be what?
Hydrogen?
Hydrogen's got the smallest numbers, right? But which one's going to be the actual smallest atom? Helium.
And why is it helium again?
Why would it be helium? There's 2 protons and 2 electrons. They're pulling on each other, right?
Mm-hmm.
So helium is going to be drawn in a little tighter than hydrogen is due to a higher effective nuclear charge. 2 protons versus 1 proton. Yep.
Is it also smaller than lithium just because it's on the energy level
Right.
closer?
So you're to find the smallest one, you got to go to the smallest energy level first, right? In other words, the highest row on the table, highest period. Everybody on the first period has got electrons only on energy level number 1, right? Once you put electrons on energy level number 2, then you're bigger than everything behind you, okay? So lithium is bigger than both hydrogen and helium. Sodium is bigger than everything on the previous 2 rows. All right, so it's got to be on the first row. Which one of those would be the smallest? The one that's furthest to the right as we look at the periodic table. But the best answer, the answer that we're looking for, is the one with the most protons. That's going to be helium. Everybody follow that? Okay, so who is the largest? Francium, the one with the most energy levels but fewest protons with that number of energy levels. So you got to go down to row 7, period 7, to find the highest number of energy levels. Which one of those has the fewest protons or the least effective nuclear charge, and that would be Francium. What we would say, the one on the left side of the periodic table. But here's the next point. So we have to be careful about using that explanation. Okay? Because, we'll put something else on the board here. The AP exam is very particular about explanations versus observations. The AP exam wants you to give an explanation, but they don't care about observations. No matter how true they might be, they don't get credit. Okay? So for example, if we gave a true statement, this is the way they like to ask questions. We're going to have some of these on the test Thursday, and these are going to be the difficult questions. Okay? So if we ask the question, don't ask the question, but give you a true statement. Neon is larger than fluorine. Sorry, that's backwards. Neon is smaller than fluorine. All right, yeah, you say it again. Neon is smaller than fluorine. Why? Okay. What you cannot say is that it's because neon is to the right of fluorine on the periodic table. That's a true statement, right? And that's the trend that we learned. The sizes decrease going across a period. But that's not a scientific explanation. It's just an observation based off of a periodic table that was designed by some crazy Russian dude in 1865. Okay? That we just so happen to put things in that order. All right? The actual explanation has to always be about structure, atomic structure. In this case, neon is smaller because it's got 10 protons and fluorine's only got 9. Okay? So here's a lesson to learn right now for all the rest of your chemistry life, whether that's this class or whether you end up doing research one day or something. Every chemical and physical property that any substance has it for a reason, and the reason is its atomic or molecular structure. That goes all the way down to why helium is bigger than hydrogen, because they are structurally different. One's got 2 protons and one's got 1. All the way up to something like 2 different proteins in your biological system. Why do they do different things? Because they have different structure. When you get up to molecular structure of proteins, there's 3 levels: primary, secondary, tertiary. It's all this globular shapes and stuff. They crystallize these things. And some of them are so big they won't crystallize on Earth. They take them to the International Space Station and crystallize them. And they do these X-ray tests on them, and they figure out what their structure is. And they're doing all this because the structure is what determines their function. But they do what they do because they're shaped a certain way. And those shapes get really complicated. You look at a picture of it, it just looks like somebody wadded up a bunch of string or something. Okay, but there's actually a rhyme and reason to how those proteins are configured, okay, what their structure is, and that structure gives them their function, okay. So we're looking for explanations based off atomic structure, not observations of where things are on the periodic table, okay. That's not the right answer, even if they're true statements. It's a true statement that neon is to the right of fluorine on the periodic table. That's not a false statement, but it's not an atomic structure explanation. So it's not wrong, it just doesn't get any points. And the AP exam is graded from, everybody starts at 0, and you're trying to get points. So if you make a bunch of true statements that aren't what they're looking for, it's not wrong, it's just doesn't get anything. So. Okay, all right, do this for me. Look at group 13, the periodic table, group 13. Tell me what order they go in, largest to smallest. What we got? Largest to smallest, group 13. Which one's largest?
Boron? Sorry, I just not. Would
Largest,
be, thallium,
largest is, was it thallium?
thallium,
All right, and then, what's that one, indium,
indium,
and then gallium, and then aluminum, and then boron, largest to smallest. Thallium's the largest, boron's the smallest, right? Okay. All right, look at row 4, period 4, P block. So P block, period 4, put those largest to smallest. These would all make excellent test questions, by the way, or quiz questions on Wednesday. What's the largest P block element in row 4?
potassium.
Just P block elements.
Oh.
All right. I know what a P block is, right?
Gallium.
Gallium is the largest, krypton is the smallest. So it goes gallium, germanium, arsenic, selenium, bromine, and krypton in that order. Everybody follow me on that? Okay. Now let's talk about why. Okay. So go back to group 13. Why is thallium the largest? Nope. That'll be the answer to the next question. So if we're in the same group, why is thallium larger than boron and everything else above it?
Energy level.
It has higher energy levels, right? Its orbitals are larger because they're higher energy. That's probably the statement to use. Its orbitals are larger because they are higher energy. Go back to the row 4, period 4 P block elements. Why is gallium the largest? Because it has less protons. Oh, I'm sorry, there we go. All right, because it has less protons, okay? It has less effective nuclear charge. So when we read phrases like effective nuclear charge, sometimes they make more sense to English-speaking people if we read them backwards. So we've not talked about how English is backwards before in here. We talked about that. Okay, so English is kind of backwards from German and French and all the rest of it. Okay. So is the charge of the nucleus effective at pulling on electrons? Okay. So you read stuff forward, then read it backwards. Sometimes it makes more sense going backwards. Sometimes it doesn't. Okay. So how effective is the charge of the nucleus? Well, it's doing what? Well, pulling on electrons, right? So the charge of the nucleus is effective at pulling electrons. The more protons you have, the more charge you have in the nucleus, so the more effective it will be at pulling on stuff. All right. What else can we talk about today? I got using stuff. Here's what I need you to do. Look at slide 106. Okay, slide 106. There's a link to a document that's about 3 or 4 pages long. Okay, here's what this is. So I was at a workshop years ago, and they passed out this piece of paper, and it was essentially a piece of paper for school teachers. And this is what you're supposed to tell your students to do and not do when it comes to periodic trends, okay? And for the sake of efficiency, I've always found it pretty easy just to forward that to the students. Like, no need to keep any secrets, okay? So this is written by people who write the AP exam, okay? And they're literally telling you what to say and what not to say for the answers to the questions, okay? All right, so they're giving you a periodic trend. It should start with atomic radius and then ionization energy, I think, okay? And there's several more that we're going to talk about. It explains the trend, and then it says when you're answering a question about the trend, say this and don't say that, okay? So those are basically generic answers to several questions on the test Thursday, okay? I will always be able to tell who does and doesn't read this because every year people answer those questions with exactly almost word for word what that piece of paper says don't say, okay? And then they get confused as to why they didn't get any credit for it. And I just point to that piece of paper and says, well, here it said don't say that, right? And you go to like word for word what they said don't say. Here's what I need you to do tonight. Read through that at least twice, okay? Read through it at least twice tonight, okay? Tomorrow, we're going to pick back up and cover the rest of the trends, okay? Talk about their explanations. We've got a couple of exceptions to the trend in ionization energy we need to talk about, and that gets a little confusing, okay? One of them especially tends to bother people. So we'll talk about that one tomorrow, try to cover the rest of the trends tomorrow. And then Wednesday, we'll take a short quiz that will not ask you to explain anything. It will just ask you to know the trends. I will give you some multiple choice questions. Say stuff, which of the following is the largest? Which of the following is the smallest? Which of the following has the highest ionization energy? Which of the following has the lowest? All of the choices will either be in the same group or the same period. We don't do any diagonal comparisons. That gets a little confusing, okay? So be able to apply the trends Wednesday for a quiz, and then we'll continue to review a little bit Wednesday and test on Thursday. All right, good with that?